So as chemists, it's not only important for us to be able to look at matter and be able to classify changes as physical or chemical, look at something and know whether it's a molecule, a compound, or just an element. All that's very important, but we make measurements of those objects. So all the matter that we have to look at and all the matter and the transformations that we have to analyze involve taking measurements. And so what we're going to do now is we're kind of going to switch gears from the situation where we're describing things and getting definitions down and go more towards the mathematical end, okay? And because we're taking measurements, what we need to be cognizant of is that those measurements have errors associated with them. And that measurement error, that experimental error, it's encapsulated in this idea of significant figures, okay? So I abbreviate significant figures as SF. So whenever you see SF, that's what that means, all right? Now there's a good example of two different thermometers on slide number 1 of PowerPoint 1. I'm going to make a slightly different argument. I mean, they're the same arguments. I'm going to make a slightly different example here. I'm going to use a slightly different example here to describe why significant figures manifest, how they manifest, and why we need to keep track of them when we do our mathematical manipulations this semester. What I have here is two different graduated cylinders. We see that there's the same amount of liquid in them. And it's pretty obvious to see here. If I wanted to get a good measurement of what the volume of that liquid is inside this cylinder, okay? Here, if I was using this graduated cylinder, I would see, well, there's some weird graduations here, but I see one at 30 and I see one at 60, right? This is a 6 here. And, so I know it's above 30 and below 60, but that's really all I can say. I can kind of guess where about it is between 30 and 60, but I don't know nearly as much as this graduated cylinder over here. So I see that this is actually a better instrument because even though the same amount of liquid is inside there, it's not now that there's this range between 30 and 60 that I'm looking at. There's this range between 30 and 40 that I'm looking at. And I can say with much more certainty that, yeah, it's definitely below 40, okay? So this is a better instrument, and we can actually get a better measurement from that instrument. So whenever we get that measurement, and whenever we use that measurement in an analysis, in doing some math, we want to represent that, hey, this came from an instrument where we knew more than, say, this instrument over here. And that's what significant figures are all about, okay? So the first thing we have to do is we have to be able to look at the measurements that you're given this semester. So we're not in the lab, so you don't have to sort of know how to get significant figures. But I'm going to give you measurements, and Chem 101 is going to give you measurements. And you need to know how to identify the number of significant figures in a given measurement. And it all comes down to whether you see a decimal place or not, right? And so then there's rules, there's sort of a logic flow that occurs. If you're looking to identify the number of significant figures, all right, and you see a decimal, then zeros at the end are significant figures. That means that zeros at the end, they matter. That means that those zeros are coming from a really good instrument. So for example, look at 500 centimeters, okay? Now this we would plug into our calculators, 500. Even how I just said it, I said it as 500 centimeters. But notice that at the end of this value here, there is a dot. There's a decimal place. Now, what that implies here is that those are important. Those are known. Those are from graduations where, yep, we're sure it's 500 point centimeters. Let's take a look at a counterexample. If you have, all right, a situation where you look at a measurement and there's no decimal place right there at all, there's no decimal point, then zeros at the end are not significant figures. So what about 500 centimeters, okay? So now what this tells us, if we look at these two values here, this tells us that we know more here, all right? We're sure about these zeros at the end. Here, these zeros, they're not significant, okay? They're coming from a worse instrument, and that's all represented with that decimal place, okay? So in the context of this example up here, even though it's not exactly the same, essentially what we're seeing here is, okay, what this must have came from is it must have came from an instrument that had more decimal places, more graduations, more known values, just like this graduated cylinder here. And this must have came from an instrument that had less known values, less graduations, right? Less information. So because we're sure about this information, we make sure we understand that we're sure by putting this decimal here. So then let's actually count the number of significant figures in each one of these numbers, and let's try to understand how this will eventually affect how we manipulate these numbers, okay? So what you do to count significant figures, you start on the left and you work your way right. Now, zeros at the beginning never matter, and we don't even have zeros written here, okay? But what you do is you find the first non-zero digit, and then you count significant digits after that, remembering this zero rule. So in this case, I start left to right. 1, 2, 3. Are these zeros significant? Yes, because of these dots. This is 3 significant figures, right? This over here, I start left to right. Okay, here's my first non-zero digit, right? Are these zeros significant? No, right? So then this actually has 1 significant figure. And again, just to drive the point home one more time, we can see it's all about the instrument it came from. Now, these centimeters readings, they didn't come from graduated cylinders, okay? Graduated cylinders measure volume, but hopefully you can kind of see the point that I'm making here, okay? This came from a worse instrument, just like in this example above, this is a worse instrument. And this came from a better instrument because we know more. There's more significant figures because it came from a better instrument with more graduations and more was known. So the first step we often need to do is identify the number of significant figures that we're dealing with to then go on and start to do mathematical manipulations with those values. All right. Just one other quick little example while we're dealing with identifying the number of significant figures. All right, here are 2 different numbers that I just wrote down real quickly. Let's figure out how many significant figures there are, all right? So you start on the left, you work your way right, okay? These zeros at the front, they never matter. So here I find the first non-zero digit, and it's 2, all right? So I count now all non-zero digits, and oh, this has a decimal, so zeros at the end would matter, right? Zeros at the end means anything literally at the end of this number here, okay? So I see that there are no zeros there, so I don't really have to worry about that rule, but it's good to have in our back pocket to use. So this has 1, 2, 3, 4 different significant figures. Zeros at the front do not matter, all right? Here I start to look and I go, okay, 1, 3, okay. So 1, 2, 3, 4, 5 significant figures, because does this 0 at the end matter, or is it just holding a place? Well, I see there's a decimal place there. And so as soon as there's a decimal place that we know that this 0 is telling us something, it's telling us that our instrument is good enough to actually know information out to that place. So this would have 5 different significant figures, okay? So hopefully you can kind of get the hang of that, because that's going to be the necessary first step when we do mathematical manipulations. And there's 2 different sets of rules when we're dealing with math and significant figures. If we start to combine information from one instrument and another instrument, we start to add things, subtract things, multiply, divide things, but the measurements are all kind of different in terms of their accuracy, in terms of their precision, then we need to represent that in our significant figure rules, okay? And we're going to break them down into 2 different sections. And the first section deals with addition and subtraction. So when you're trying to figure out significant figures in a mathematical process, the first thing you ask yourself is, am I doing addition and subtraction or multiplication and division? If the answer is you're doing addition and subtraction, there's a different rule, all right? Subtraction, all right? The rule for addition and subtraction deals with decimal place, all right? You're limited, so your answer is limited by the least precise measurement. Now, what that means for us in a practical sense is you look at the decimal place. Now, by decimal place, we could mean before the decimal point or after the decimal point, and the decimal point might not even be present, right? You kind of just have to make sense of what that decimal place means from math courses. It's the same thing here. You're limited by the least precise measurement, right? So your answer can only have the same decimal places as the worst measurement that you're manipulating, right? Which kind of sounds a bit confusing until you do a couple examples, and so that's what we're going to do right now. So let's say we had 32.33 degrees Celsius, and then we also had 32.3 degrees Celsius. These must be coming from two different thermometers. Now, how do I know they're coming from two different thermometers? This thermometer over here can get me information out to this place, but this thermometer here can only get me information out to here. So I plug these into my calculator, and what I get is 64.63 degrees Celsius, right? So that's pretty easy, but now what we have to know is how many significant figures would be in this number. We have to be smarter than our calculator. Our calculator spits this out, and now we have to apply our idea of significant figures to this number. So we ask ourselves, what math did we just do? We did addition and subtraction. This is good to the hundredths place, 2 spots past the decimal. This is good to the tenths place, just 1 spot past the decimal. So my answer here is only good to 1 spot past the decimal. This is the worst measurement. I only know information to 1 place behind the decimal point, so my answer can only be known to 1 place by the decimal point. Now, what I like to do is I like to underline my significant figures, because we're going to have this rule where we round at the end. And so we always keep track, and we keep track of the significant figures that we have. We keep all non-significant digits until the very, very end. All right, you'll see that in a further example, but we're going to kind of get used to doing it now. So I'm going to underline everything up until that point, because that's what the addition and subtraction rule is about, decimal place. And my final answer that I report is rounded to that spot. So my final answer would be 64.6 degrees Celsius. Now, why do I not make this 64.7? Remember our rounding rules, this would have to be 5 or higher to bump this up. It's not, so my final answer is 64.6 degrees Celsius, right? So it's all about decimal place, right? Let's take a look at, right, 500 centimeters plus 600 centimeters, okay? All right, so now this is a really interesting problem. We can plug this into our calculator and we get 1100 centimeters, we get 1100 centimeters. But we want to make sure that we're representing significant figures appropriately, okay? Is that value that comes out of our calculator correct? Well, this looks like it actually comes from the same instrument, because this is good to this place. Now, what do I mean by that? Okay, I like to draw arrows to show the place that they're good to. Well, are these 0 significant digits? No, they're not significant digits, okay? So this is good actually to 3 places to the left of the decimal place, and the decimal place doesn't have to be there, do you know what I mean? So hopefully you kind of see what I'm saying there, okay? The decimal place doesn't have to be there to recognize that this is good to 3 places past where it would be, all right, to the left. Same thing here, it's the same accuracy, okay? It's 3 places to the left of that decimal. So when I come down here to my answer, okay, this is good to 3 places to the left of the decimal. This is good to 3 places to the left of the decimal. They have the same precision, all right? So my answer here is good to 3 places to the left of the decimal. I always start working left to right with the number of significant digits that there are. Okay, so yeah, this is a situation where this number that comes out of our calculator, I would underline these two because they're both significant digits. This decimal place matches with this decimal place, all right? So my final answer is 1100 centimeters, and that's actually it, and you're done. So just by doing our significant figure check, we see that in this case, what our calculator spits out is the actual correct answer, 1100 centimeters, all right? We could write this in scientific notation. 1, 2, 3, ooh, 10 cube, all right? And the good thing about scientific notation, which is something that you're familiar with, but I just want to do a quick little review, is scientific notation gets rid of those non-significant figures. The nice thing about scientific notation is that anything that's insignificant, the rule for scientific notation is you just get rid of it. Just like these zeros wouldn't matter here, these zeros wouldn't matter here, our answer has zeros that don't matter at the end, they're insignificant. What we do to write this in scientific notation is we're going to move the decimal place, and we're going to move the decimal place 1, 2, 3 spots. So I'm going to write this as times 10 to the third, right? Because we have this big number here, but I'm only going to include 1.1, right? I'm only going to include my significant digits there. Scientific notation is always a number, a dot, and then all your significant figures. Were these zeros significant? No. So I'm only going to write this as 1.1 times 10 to the third. And we'll do more scientific notation practice as we do other examples. So just a quick little recap for addition and subtraction. It's all about the decimal place, right? So what is our rule then for, right, multiplication and division? So again, the thought process is, all right, I'm keeping track of significant figures. I'm doing some math. For every step that I do, I ask, is it addition and subtraction, or is it multiplication and division? Because there are different rules for each, right? So the rule for multiplication and division is easier. You're not paying attention to decimal place. You're paying attention to total number of significant figures. Your answer has the same significant figures as the number with the smaller amount of significant figures that's involved in the multiplication or division. So this is not about decimal place. This is about counting the number of significant figures, right? Counting the number of significant figures. Don't confuse the rules. So once you learn this rule, students have an easier time getting comfortable with this rule. Do not use this rule for addition and subtraction. This only applies for multiplication and division. One more time, addition and subtraction, it's about decimal place. Multiplication and division, it's about number of significant figures. So just kind of show you what we mean here. Let's do an example. All right. So let's take 32.33 degrees Celsius. And now let's multiply it by 32.3 degrees Celsius. Right. So this is a multiplication problem. These units you'll see are very vital to our understanding of how things work. This dimension, these units here, they come along for the ride as a variable. I'm going to plug this into my calculator, but the calculator is going to spit out a number, and I'm going to have to know myself what the correct significant figures are and what the correct units are. All right, so I have to be smarter than my calculator here as well. So when I plug this in my calculator, what I get in scientific notation, okay, and I'm not going to round quite yet, I get 1.044259 times 10 to the third, okay? So now let's add in our extra bits of information that we need to make sure that we're getting the correct number of significant figures and the correct units. Let's do units first. Units are variables, right? If I take a variable and I multiply it by itself, all right, essentially what I've done is squared that variable. If I have an x times an x, what do I get? I get an x squared. So for this multiplication, what I would get is a degrees Celsius squared. This times this makes it squared. Now I look here. This is what my calculator spits out, okay? And it's in scientific notation already, okay? But I need to know, are these digits, are all of them significant? Which ones are significant? I ask myself what math I did. The math I did was multiplication division. So I go back to the numbers that I multiplied and I look at the number of significant figures inside them, the total number of significant figures. So I look here and hopefully you can recognize that there would be 1, 2, 3, 4 significant figures here. There are no zeros. We don't really have to worry about the zero rule here. It's literally we count all those digits, okay? There's 4 significant digits here. Here there are 3 significant digits, 3 significant figures. So when I go down here to my answer, right, this has 4 significant figures. This has 3 significant figures. So whenever you do that counting, your answer has the lower amount that you count. So because this has 3 significant figures, then that means my answer will only have 3 significant figures as well. So at the end of this problem, what I'm going to do is I'm going to round again, okay? I look here, there's a 4 here, so I'm not going to bump this up. My final answer is 1.4 times 10 to the third degrees Celsius squared. Okay. So really important idea here, okay? When we do multiplication and division, it's a little bit easier because you're going to get really good at identifying the number of significant figures. Whichever one is smaller in the values being manipulated, whichever has the least significant digits, that's the same in the answer. Do not use this rule for addition and subtraction, but for multiplication and division, you can see now how it plays out. The only other thing that we really need to know, just kind of getting a basis for use of significant figures in our calculations, is whenever we have a multi-step calculation, and I kind of mentioned it earlier, but it's important to know and go over with an example, is you round at the end. Which means that you carry all your digits through, but every time you do a mathematical step, you check significant figures. All right. At the very end, when you're done, is when you start to drop things off and when you round to the correct number of significant figures. So this is easiest to see again with an example. So let's look at 32.33 degrees Celsius plus 32.3 degrees Celsius divided by 100 grams minus 50.0 grams. This is a multi-step calculation. One thing that students will try to do is you'll try to look at this from the start and decide how many significant figures there are in the end. Do not do that, all right? Our rule is we do every step one at a time. You check at the end of every step. You keep all digits until the very, very end. You only round at the end. So for example, how would you handle this problem in a math class? Well, I would have to do the top of the fraction first, and then the bottom separately, and then finally there would be this last step where I do the division. So let's do each step one at a time and keep track of significant figures along the way. We did this math before, right? So we got 64.63 degrees Celsius out. Just to remind you, if we ask ourselves in the numerator here, what math are we doing? We're adding, so decimal place matters. This is good to this decimal place, this is good to this decimal place. Oh, that means that my answer is only good to that first decimal place, okay? Am I going to round this now? No, we only round at the end. So even when I go on to subsequent steps, am I going to consider this 3? Yes. We're not at the end of the problem, so we're going to keep that 3. But notice, I'm keeping track of how many significant figures I have because that will matter at the end of the problem. All right? I'm going to show the division with green here just so you don't confuse my underline with the division bar. What math is this down here in the denominator? It's subtraction. So what rule matters for subtraction? It's all about decimal place. Oh, are these zeros significant? Yeah, because that decimal place is there. Okay, so then this number is good to that place. It's good to the ones place. Okay, so then I look here, 50.0. Is this 0, does it matter? Does this 0 matter? Well, yeah, both these zeros matter, again, because there's a decimal there. This number is good to the tenths place. Which number is actually better? Well, the number that's actually better is this. This came from an instrument where we can actually get all the way out to the tenths place, where this instrument gave us information just to the ones place. So when I plug this in my calculator, I get 50. But that's not how I should write that, because this is good to the ones place, this is good to the tenths place, so my answer should be good to the least precise measurement. The same decimal place as the least precise measurement. My answer should be good to that place as well. Now, how am I going to make that 0 significant? How am I going to remind myself that that is a significant digit? I'm going to put a decimal there, and I'm also going to underline. Okay? So it's all about making sure we use our rules one step at a time, keeping track and only rounding at the end. So even though my calculator spits out 50, I know I really should write it as 50 point. The units come along for the ride as a variable, okay? Now my final answer I can get by taking 64.63. I use that 3, but I know that only 3 of these digits are significant. I plug that in my calculator, I divide by 50, what I get is 1.2926 degrees Celsius per gram. Those are not the same value. Those are not the same unit, so they're not going to cancel. All right. I get this value out in my calculator, but then think about this last step. What was the math? Addition, subtraction, or multiplication, division? It was division. So now what matters is total number of significant figures. In the bottom here, I have 2 significant figures. In the top here, I have 3 significant figures. So my final answer only has 2 significant figures, right? So I would write this as 1.3 degrees Celsius per gram. If the problem asked me to write this in scientific notation, it kind of already is in scientific notation. You could write this as, and I'll just write it to the side here. You could write this as 1.3 times 10 to the 0 degrees Celsius per gram. But honestly, that means the exact same thing as this because 10 to the 0 is 1. So everybody can kind of see with this example, it's a very important example, what I mean by round at the end. You keep track of your significant figures along the way. You use those insignificant digits in the calculation because at the very end, that's when we go ahead and truncate our number to the correct number of significant figures. If you look here at the beginning, all right, I just want to point out a common error. Again, some students would look at this and try to guess the number of significant figures. None of these values just have 2 significant figures. Do you know what I mean? Like, you're never going to get the correct significant figures if you just go ahead and guess from the start. You keep track of significant figures along the way. At the end of each math step, you underline the significant figures, keep in significant figures until the very, very end. And then that's when you round to the correct number of significant figures, right? It takes a lot of practice, but you're going to do that practice. Significant figures are going to be used in most every calculation that we do. And so it's really important that you develop it as a skill, as a tool that you know how to enact properly, and that you're really comfortable with using.